In tutorial number 6, we'll cover the shearing stress in beams. In the previous chapter, we seek to find the maximum normal stress from bending, where the normal stress itself is given by my/I. In this chapter, we'll seek to find the maximum shear stress tau equals to VQ/IT. We are now familiar with the shear and bending moment curves, as you can see over here. If we consider a section of the beam, we find that for moment curve itself at the bottom, the left and the right side of this element here will be different. We can draw it here such that the left moment is lower and the right moment is higher. We know previously that moments causes normal stress. Hence, we can draw the normal stress due to the bending moments as such. The moments over here will cause compression on top and tension below. Here as well, compression on top and tension below. The normal stress on the right hand side is larger because of the larger moments over here. We are able to cancel the left and right side, and as such we arrive at the normal stress that's having this distribution along that section of the beam. We redraw the section here with the associated forces. We can assume this section to be made up of different layers. Layer 2 itself will try to prevent layer 1 to slide to the left due to the forces. As such, there will be a shear stress between layer 1 and layer 2. Layer 3 over here will try to prevent layers 1 and 2 from sliding to the left. As such, there will be a shear stress here which is larger because it's trying to withstand or prevent the sliding from the forces on 1 and 2. Same thing for the shear stress between 3 and 4, which is going to be much larger. If we were to draw the shear stress across the different layers, it will look like this, where the shear stress is smallest towards the ends and largest towards the center. For beams in bending, the maximum shear stress is thus at the center. And we can use tau equals to VQ/IT to solve. V is from the graph, Q is the first moment of area, I is the second moment of area, and T is the thickness of the cut. Say you have a beam section below. If you want to find the shear stress at that location over here, this location itself, the thickness, will be T in your VQ/IT. The value of Q is just the area above where you cut, over here that's the area, multiplied by the distance between the neutral axis of this area to the neutral axis of the entire cross-section, which is given by Y over here. As such, Q is equals to area times Y. We can also consider the area below the cut, which is this area, and Y itself is given by this Y, both of which will give us the same answer for Q. Maximum shear stress for different cross-sections will be at different points. For symmetric sections, maximum shear stress is at the neutral axis if the neutral axis is also the smallest cross-section. Otherwise, maximum shear stress will be at the junction. We have a few cases here. First, we have an I-beam. For the I-beam itself, the neutral axis also has the smallest cross-section or the smallest value of T. Therefore, the maximum shear stress is at the neutral axis. For this plus sign, which is also symmetric, the neutral axis does not have the smallest T or the smallest cross-section. Therefore, maximum shear stress will be at the junction. We will need to calculate the maximum shear stress over at the neutral axis as well as at the junction. We need to calculate both of them so that we are very certain that the values that we obtain for the shear stress is the maximum. For non-symmetric sections, it will actually depend. Over here, the neutral axis itself is not the minimum thickness T. Therefore, maximum shear stress may be at the neutral axis or maybe at the junction. We'll need to calculate both. For this T shape here, because the neutral axis is also at the smallest cross-section, therefore the maximum shear stress is over here at the neutral axis. The first moment of area for circular cross-sections can also be derived. For solid section, it is 2r cubed over 3, and for hollow section is given here. We will now look into the tutorial. In this question, we will need to find the largest shearing stress in the cross-section of the beam and the shearing stress at point A over here. We need to first draw the shear and bending moment curve. Step 1 itself is to draw the free body diagram. The free body diagram of the beam can be drawn as such, where at the free end itself, which is attached to a wall, we have a shear and the bending moments. As we do not know the values or the direction, we assume a positive convention. In step 2, we will need to find the reaction forces. As such, we take the summation of moments about this point over here, and then we find that the moments is equals to negative 15 kilonewtons meters. We also take this summation of forces or shear to be 0, which is V minus 10. As such, V itself is equals to 10 kilonewtons. In step 3, we will draw the shear and bending moment diagram for the beam. We will follow the rules that we have seen previously. First of all, over at this end itself, because it is attached to a wall, as such moments and shear are non-zero. Shear itself will start at 10 because over here V equals to 10 over at this fixed end, and it will be a straight line all the way to the end before you go back down to 0. For moments itself, it will start at negative 15 because moments is calculated to be negative 15. Over here, it will have a positive gradient all the way to 0 at the free end, as you can see over here. The gradient itself is equal to the value of shear, as in rule 1. As shear itself is 10, as such the gradient here is 10. For the maximum shearing stress, it will be at the neutral axis for this I cross-section, because the neutral axis at the center is also the location of minimum thickness. To find the shearing stress, we will make use of the equation tau equals to VQ over IT, where V was from the shear graph. T itself is equals to 100 mm over here. To find the moment of inertia, we will be able to use two methods. Let us talk first on this method of using sections 1 and sections 2. To find the moment of inertia, we will take the moment of inertia for section 1 over the neutral axis plus 2 times the moment of inertia of this top section 2 plus 2 times that of the parallel axis theorem to shift the axis to the neutral axis of the whole object. Alternatively, we can also consider subtraction. If we consider this whole object and then we subtract away the area here, we can arrive at this. This itself is the moment of inertia for the entire object, and we minus away these small sections by the side. As such, this section is B1 H1 cubed over 12. This section is B2 H2 cubed over 12, which we can insert in the known values and we get the moment of inertia as such. To get the largest shearing stress, which is at the neutral axis, we will take Q at the neutral axis. We consider the cross-section above the neutral axis. We break it down into sections 1 and sections 2. Q itself will be the area of 1 multiplied by the distance between the neutral axis of 1 to the neutral axis of the whole object, plus the area of 2 multiplied by the distance y2, which is the distance between neutral axis of 2 and the neutral axis of the whole object. Substitute in the known values and we obtain this value for Q. For shear stress itself, the equation was given previously. We now know the values of Q, I, V, and T. As such, we can solve and obtain 920 kilopascal. At the section A here, for part B of the question, we take the cut at A. As such, this is what we obtain. We will consider the section above it. We find the value of Q as 302.8 times 10 to the power minus 6 meters cubed. And then we substitute in the value of tau and we obtain 765 kilopascal. In this next question, we have a beam over here and we are told to find the width B subject to the allowable normal stress as well as the allowable shear stress. We will first need to plot the shear and bending moment curves. In step 1, we draw the free body diagram. We have the reaction forces at A and the reaction forces at D. In step 2, we try to find out what are the reaction forces. We take the summation of moments about D and we obtain RA equals to 2 kilonewtons. We take a summation of shear forces to be 0 and we find that RD is 12.4 kilonewtons. In step 3, we will use the rules here to obtain the shear and the bending moment plots. On the left end, this is pin, as such shear is non-zero, moments will be 0. Shear itself will start at 2 kilonewtons. In between point loads, a straight line, then it will drop by 2.4, and you'll be a straight line all the way here, and you'll drop by 4.8, and then a straight line in between point loads, and then you will go up by 12.4 all the way to 7.2, and then go to the end of the beam and go back down. For moments itself, we can make use of the first rule, which is the slope of the moments is shear. Shear here is 2, therefore the slope of moments here is 2. Then this is negative 0.4 for the slope, and it becomes negative 5.2 for the slope, and then positive 7.2 for the slope, and you will end at 0 moments. To obtain the value of the moments, this itself is just the area under the shear curve, which is given by the rule number 2. There are two conditions of maximum normal stress and maximum shear stress given by the question over here. We'll first look at maximum normal stress. As the beam itself undergoes bending, there will be normal stress due to bending, and the maximum normal stress itself will be over at the surface. From the equation sigma equals to my over I, y itself is at the surface and is equals to h over 2. I will just be the moment of inertia about the horizontal axis, and this is b h cubed over 12, and this is b. We can manipulate the equations and arrive at this form. Substitute in the known values and we obtain b equals to 80 mm. For the second condition of maximum shearing stress, as the object itself is a rectangular, the maximum shearing stress will occur right at the neutral axis at the center. Using the equation of maximum shearing stress, tau equals to VQ over IT. Q itself is just the multiplication of the area above the neutral axis and the distance between the neutral axis of this area as well as the neutral axis of the whole object. It is area times y. T itself is the thickness of this cut. Now, we just need to manipulate the equations, substitute in the known values for Q, which is A times Y, I, which is VHQ over 12, and subsequently we manipulate the equations and we arrive at this form, which is 3 over 2 V over BH. We substitute in the known values and we find that B equals to 87.3 mm. We now have two dimensions, and for cross sections we will normally choose the larger one, which is 87.3 millimeters. For this question, we have a beam with a concentrated load at the center. We are told to find the ratio of the maximum shearing stress to maximum normal stress to be equals to H over 2L. We are also told to find the width and the depth of the beam. We can first plot the shear and bending moments curve, which we have gone through in the previous lecture. From the previous question, for rectangular cross-section, the maximum normal stress is given by this expression. Also, from the moments curve itself, we find that maximum moments is at PL over 4. As such, we substitute moments equals to PL over 4 into this equation and we arrive at this form over here. Rearranging, we obtain this form. For maximum shearing stress, we can also obtain from the previous question and tau m equals to 3V over 2BH. We obtain the maximum shear from the shear curve, which is P over 2, and we substitute it inside as given here. And we arrive at this expression. Then we take the ratio between tau m and sigma m, and we insert this and this into the equation, and after some manipulations, we arrive at H over 2L. To obtain the values for H and B, we will use equations 1 over here and 2 to obtain H equals to 320 mm and B equals to 97.7 mm. In this next question, we have a beam that is supported by pins and we have 2 point loads at the center. We are told to determine the shearing stresses at points A and B along the cross section. We first draw the shear curve as shown here. By now, this should be easy for you to draw. To get the maximum shearing stress, we must obtain the value of the maximum shear from the plot, which is 50 kilonewtons. In the equation VQ over IT, V is 50 kilonewtons, and we need to find what is Q and I. To do so, we'll first need to find out where is the neutral axis. The neutral axis can be obtained from what we have studied before, where A1y1 equals to A2y2 equals to the total area multiplied by the neutral axis. We break up these cross sections into section 1 over here and section 2 over here. And then we substitute the known values for these two sections into the equation and we obtain y neutral axis is 0.05 meters from the bottom, which is given here. Just nice, the neutral axis occurs in between 1 and 2. To obtain moment of inertia, we will use the moment of inertia equation about the base of a rectangle, which is BHQ over 3. We will find the moment of inertia for section 1 about the base over here, and moment of inertia for section 2 about the base over here. As both of them share the same axis, therefore we can sum them together and obtain the moment of inertia as such. To obtain the shear stress at A, we will cut a section at A and take the top part, as it is over here. To obtain the first moment of area Q, it will be equals to the area of this section multiplied by the distance from the neutral axis of the section to the neutral axis of the entire cross-section, which is given by this value here. And subsequently, we obtain Q. Substitute in all the known values to tau, and then we obtain tau equals to 8.75 megapascal. We can do the same for point B, where Y itself is now 75 millimeters and the area is larger. This is the value for Q. Substitute in the known values to tau and we get 15 megapascal.